Right, we're going to take a look at one more example of what happens when you pull conductors through magnetic fields. What's happening here is you've got this conducting bar that's being kind of pulled at a constant speed, like in a circle. So things being kind of swung around like a propeller about this point. Here's the axis, and this thing is going to be pulled at a constant speed. And so the first thing that we're supposed to do here is figure out which end of the bar would be like the positive end and which would be the negative end. Well, so what's going to happen is if you imagine positive charges in this thing, so imagine a positive charge. Well, if you, at this instant, that positive charge is moving this way. That's the direction of the velocity of this positive charge. There's V. The positive charge is moving that way through a field that points into the page. So what's going to happen is there's going to be a magnetic force on that positive charge this way. So this would be F magnetic on a positive charge, which of course is going to be like QVB. Likewise, you know, the electrons, right? If this is an electron, you can use left-hand rules on those. Electrons being pulled that way through fields that point in will get pushed to the other end. And so what's going to happen is this side of the stick is going to become like the positive end, and this side of the stick is going to become the negative end, right? So you're going to get this voltage difference between the two ends of the stick. Well, so what we can do like last time is we could figure out how much work it takes to move a charge from one side to the other, okay? So the work in that case, we know that work is force times distance. But the deal here is that the force is going to change as you move because the velocity of a given charge is going to be different or greater when you're way out here, right? Something way out at the end is going to be going much faster than a charge that's in here, okay? And so since we have a varying force, what we're going to have to do is we can't just simply multiply a force times a distance, but we're going to have to integrate, okay? So the work is going to be the sum of force times a little bit of distance. Okay, a little bit of work would be force times a little bit of distance. Maybe I should have even written it that way. Like a tiny bit of work would be force times a tiny bit of distance. And then you just got to add them up. Okay, so that's what we're going to do. So let me move this just a touch. There we go. So what we need to do then is add up the magnetic force, which is QVB, times that little bit of distance. And we'll go all the way, say, from the inside to the outside, all the way from 0 to L, all the way from the inside to the outside. This velocity is going to depend on how far out you are. Right, so from mechanics, right, we know that V equals R omega, and so this is going to be Q, basically R omega B dr, all the way from 0 to L. So it looks like we're ready to add these up or to integrate. And so what we can do, let's pull the constants out. Q, omega, and B are all constants. And then we just need to integrate R from 0 to L. R. And so finally you get, well, that's going to be R squared over 2, so L squared over 2. So you get Q omega B L squared over 2. And then what we can do to just wrap this up, so that's supposed to be the amount of work done. Then what we can do to get the voltage difference between the two ends is voltage difference is work per charge. So your delta V, which is work per charge, well, that's just going to be this thing divided by the charge. So that's going to be omega B L squared over 2, because divide this by charge and you get rid of the Q. Then what we can do is put numbers in for this thing. So numerical value for the voltage for the parameters given in the problem. It looks like if we've got this thing rotating once per second, that would be an angular velocity of 2 pi radians per second. times a magnetic field B, which is 2 Tesla, times the length squared. So this was given to be a long rod, 3-meter rod. So that's going to be L squared then would be 9. And then divided by 2, as in the expression. And then you can see that the 2 and the 2 pi and the 2 in the denominator will cancel. So in that case, we'll end up getting, 18 pi as the voltage difference between the two ends. So 18 times a little bit more than 3 volts. And so that would be the voltage difference between the positive end here and the negative end here, which is up toward the upper right. As an interesting little tidbit to add to this problem is we've seen that another way to get voltage or induced EMF is to look at the change in flux with time. Now, of course, there's not really a change in flux in this case because there's just a metal bar that's kind of being swept around. But just an interesting way to look at this is if you think of flux, of course, as field times area. But then think about the relevant area for this problem being like the area that's like swept out by this thing as it moves, as this thing cruises around. Well, if you take a close look at this, you'd have a change in flux or change in field times area with time. The field is remaining constant, so this would just be B times change in area with time. So in other words, we just have to figure out the rate at which the area that's swept out is changing as this thing cruises around in a circle. Well, so if you think of the area being an entire circle, if this thing's rotating once per second, then what we can do is say, well, we have the field times an area of pi r squared or pi l squared, and then that occurs over a time interval of 1 second. And so what you see if you do it this way is you'll get B times pi l squared as the voltage difference between the two ends for this case where the thing is rotating at once per second. And so then in that case, right, if we just put in the numbers like we did before, field was 2 Tesla times pi times the length squared was 9 because it was 3 squared. So you get 18 pi volts. Again, so it's just another way to view this, that you could either think about how much work does it take to drag one charge to the other side, and then say the voltage difference is work per charge, or you can kind of take this other view about thinking about the swept out area, and use the voltage difference between the ends is going to be the change in field times that swept out area per time.